Hey everyone, and welcome to the Deep Dive. Ready to explore some seriously cool science today? We're going to be diving into the world of matter and all the crazy ways it can change. Ever wonder what's actually going on when, say, you melt an ice cube or you bake a cake? There's some serious science behind it. And today, we're going to break down the difference between two big categories: physical changes and chemical changes. By the end of this deep dive, you'll be able to tell them apart like a pro. So let's kick things off with some examples. Think about crushing a can, melting ice, or dissolving sugar in water.
It's fascinating. In each of these cases, you're changing how the substance looks.
Right.
But you're not actually making something totally new. You can still tell it's the original substance, even if, it's a bit different.
Right, it's like rearranging furniture. It's still the same stuff, just in a different spot.
Exactly. And most of the time, you can actually reverse a physical change. You can refreeze that melted ice, get the sugar back from the water. You can even try to undent that can, although that might be a bit of a workout. The key is the chemical makeup of the substance is still the same.
Okay, so let's get a solid definition here. A physical change is a change in how the substance looks, but not in its chemical composition. And these changes are often reversible.
Ah.
Got it. Good. All right, now let's turn up the heat, literally, and explore the world of chemical changes. We're talking things like burning wood, iron rusting, or even that classic baking soda and vinegar volcano.
Now, these changes, they're a whole different ballgame. We're not just talking about appearances anymore. We're talking about transforming the substance at the molecular level. You're creating something entirely new.
So basically, in a chemical change, you get brand new substances with completely different properties than what you started with. And often, these changes are irreversible. You can't unburn wood or unbake a cake. Let's try and define this one too. A chemical change is when substances combine or break apart to form new substances. These changes are, like we said, often irreversible. Makes sense.
Perfect.
Okay, let's take a closer look at one of those chemical change examples. Baking soda and vinegar. What makes this reaction so special?
Well, it's a really cool example of how chemical changes can create something totally different from the original ingredients. So you have baking soda, which is a base, right? And then you add vinegar, which is an acid, and bam, they react to make carbon dioxide gas, water, and a salt.
You got it. And you can actually see this change happening, those fizzing bubbles. That's the carbon dioxide gas escaping. It's like a tiny science experiment in your kitchen. So before we move on, any questions about physical and chemical changes?
I actually have one. How can you be absolutely sure if a change is physical or chemical? Are there any, telltale signs?
That's a great question. It's not always easy to tell just by looking, but there are some clues you can look for. Like if the color changes or you see a gas forming, like those bubbles we talked about. Or even if the temperature changes or a solid forms from a solution. Those can all be signs of a chemical change. But to be 100% sure, you'd have to analyze the chemical composition before and after the change. All right, let's shift gears a bit and talk about another fascinating chemical change, something we've all seen. Rust. That reddish-brown coating you get on old iron objects. But what's really happening on a tiny molecular level?
Yeah, rust. It might look pretty simple, but it's actually a pretty complex chemical reaction. We're talking iron, oxygen, and water all playing a part.
Exactly. It's not just air that causes rust. Moisture is key, too. Think about it. A car will rust way faster in a humid place than in a dry one.
Oh, and here's a fun fact. Salt water makes rusting happen even faster. That's because salt water conducts electricity better, and that makes it easier for the iron to react with oxygen. That's why things like ships need extra protection, because they're always in salt water.
So let's break it down. When iron hangs out with oxygen and water, it goes through a chemical reaction called oxidation. The iron atoms lose electrons, and the oxygen atoms grab them. And that creates iron oxide, which is that reddish-brown rust we see.
And here's the thing. Once rust gets started, it can actually spread and make the metal weaker. Eventually, it can even break down completely. That's why preventing rust is so important, especially for things like bridges and cars and tools, things we need to stay strong.
All right, definition time. Rusting is a chemical process that happens when iron, or an alloy with iron in it, like steel, is exposed to oxygen and moisture for a while.
Got it.
Any burning questions about rust before we move on?
Actually, yeah, I do have one. We've talked about how to stop rust using paint and grease, but are there other ways to protect iron from corrosion?
Absolutely. There's this cool process called galvanization. Basically, you coat the iron with zinc. Zinc is more reactive than iron, so it acts like a shield. It corrodes instead of the iron. You'll often see this on things like guardrails and fences. All right, let's move on from the rough and tumble world of rust and talk about something a bit more sparkly. Let's talk crystals.
Ooh, crystals. They're not just beautiful to look at, they're like a window into how incredibly ordered and precise nature can be.
Okay, back to basics. What exactly is a crystal?
A crystal is a solid material. But here's the thing. Its atoms, or molecules, are arranged in a super-organized pattern that repeats in all directions. This repeating pattern is called a crystal lattice, and it's what gives crystals those cool geometric shapes.
So unlike most solids where the atoms are all jumbled up, in crystals, they're lined up neatly, like picture soldiers in formation.
Exactly, and that organized structure gives crystals their unique properties. Like, think about how hard diamonds are and how they sparkle. That's all thanks to their crystal structure.
So how do these amazing structures form? It's called crystallization, and it's a fascinating example of a physical change.
Right. Crystallization can happen in a few ways. One common way is to dissolve a solid in a liquid, like salt in water. Then you let the water slowly evaporate. As the water goes away, you get more and more of the dissolved stuff left behind. Eventually, the solution can't hold anymore, and the extra stuff starts to come out of the solution as crystals.
So it's like making rock candy. You dissolve tons of sugar in water, let the water evaporate slowly, and bam, you get those beautiful sugar crystals.
Exactly. And the slower the water evaporates, the bigger and more well-defined the crystals will be, because those molecules have more time to arrange themselves in that perfect pattern.
Okay, definition time again. Crystallization is the process where a solid forms and its atoms or molecules are arranged in a superorganized structure called a crystal. Clear as crystal. Got any questions about crystals before we move on to the next fascinating topic?
I do have one, actually. We've talked about growing crystals from solutions, but like, are there other ways they can form?
Oh, that's a really good question. Yeah, crystals can also form from a melt, like when molten rock cools and solidifies. Think about those amazing crystals you find inside geodes. They formed over like millions of years as that mineral-rich water seeped into those cavities in the volcanic rock. And as the water slowly evaporated, the minerals were left behind and crystallized. Pretty cool, huh? All right, let's switch gears again. This time we're going to talk about a chemical change that's maybe not as glamorous, but definitely just as important. Let's talk about burning magnesium.
Oh, yeah. We've all seen those awesome fireworks displays, right? Those bright bursts of light and color. But have you ever thought about the science behind all that?
It's all thanks to a chemical reaction. When magnesium burns, it reacts with oxygen in the air. And that doesn't just create that brilliant white light, it also produces a ton of heat.
Right. And what's left after all those sparks fade away? A fine white powder, totally different from that original magnesium ribbon.
And that powder, that's magnesium oxide. It's a brand new substance that's formed when the magnesium and oxygen combine.
Yeah, it's a classic example of combustion. That's a process where something reacts really quickly with an oxidant, usually oxygen, and creates heat and light.
So the next time you see fireworks,
Yeah.
remember, you're watching some serious chemical changes in action. Okay, let's get a definition down. The burning of magnesium is a chemical reaction between, you guessed it, magnesium and oxygen. It makes a super bright white light, a bunch of heat, and that white powdery stuff called magnesium oxide. Makes sense. Good. Any questions about burning magnesium?
Yeah, I have one. So how is burning magnesium different from rusting? Because they both, they both use oxygen.
Ah, great question. So while both processes do use oxygen, the speed and the intensity of the reaction are totally different. Burning happens super fast and it releases a ton of heat and light, remember. But rusting, that's a much slower process. It takes a long time to happen. Plus, don't forget, rusting needs water to get going. Okay, let's dive into another example of a chemical change that we see every day. Milk going sour.
Ugh, we've all been there, right? You open the fridge and you get hit with that sour smell of spoiled milk. But what causes that to happen?
It's all those tiny little bacteria. When milk sits out at room temperature, bacteria start to multiply like crazy, and they break down lactose, which is the sugar in milk. And when they do that, they create lactic acid.
And that lactic acid is what gives spoiled milk that sour taste and smell. It's a chemical change because the milk itself has been changed. It's not just different in how it looks, it's created new stuff with different properties.
All right, let's define the souring of milk. It's a chemical change that happens when bacteria break down the lactose in milk and produce lactic acid. That's what makes it taste and smell sour. Any last questions before we wrap things up?
Yeah, just one more. We've talked about, all these changes today, but what's the big takeaway? Why should we even care about the difference between physical and chemical changes?
That's a great question to wrap things up with. Honestly, understanding the difference helps us understand the world around us. It explains, like, how things work, from cooking to the weather to even the things happening inside our bodies.
Mm.
Plus, it lets us kind of control and use these changes to our advantage. Think about, like, developing new materials or preserving food or even making those awesome fireworks displays.
Right. It's all about appreciating how complex and beautiful the world around us is, from the smallest atom to, the biggest star.
So, there you have it, a deep dive into the fascinating world of physical and chemical changes. We hope you learned something new today and, more importantly, that you're inspired to keep asking questions and, to keep exploring all the amazing things science has to offer.